तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The question has been raised as to whether the Lyapunov exponent is independent of the initial condition or not. Now you see the situation is as follows: if this is your big phase space and you start with some point here x0 and it undergoes a trajectory of this kind, this point lies on a trajectory of that kind, then if this initial condition is such that this trajectory comes arbitrarily close to almost all points in phase space, then of course as time goes along it is quite clear, if I take the infinite time limit and compute the infinite time Lyapunov exponent, you have explored all of phase space in some sense. Therefore in that sense it should become independent of x0 itself. However, we have to remember that it is entirely conceivable that this part of this initial condition is stays in some region of phase space, some attractor, and there could be another attractor in another portion. Initial condition starting here could stay here, in which case the Lyapunov exponent would depend on where you are. So in general of course it depends on where you are in phase space, but our assumption is in the simple models we are looking at, any arbitrary initial condition, if it is sufficiently generic, is going to eventually its iterates are going to fill up the phase space and come arbitrarily close to all points in phase space. So we have assumed ergodicity of some kind. You might have multiple attractors, this could very well happen, there are situations, many situations where it does, but otherwise this statement is certainly true. The other point is the Lyapunov exponent is now a property of the trajectory rather than of the initial point itself. That much is clear, that you are trying to find out the average exponential separation along this trajectory as you go along. Okay, we had looked at the case of the Bernoulli shift, and I pointed out that its Lyapunov exponent was log 2 and that it was positive, and we had an invariant measure which was constant, an invariant density which was constant. Now let us look at a situation where you have a measure which is preserved, namely something like a Hamiltonian flow, but which is still chaotic. So it is a very simple model of a conservative system, discrete time system, where you would have something mimicking the Hamiltonian in the sense that volume elements are preserved or area elements are preserved, but at the same time the system is chaotic, and it is done by a very simple extension of the Bernoulli map. It is called the Baker's map. And it is modeled on the way a baker needs dough to make bread. So what the baker does is to take this piece of dough and he stretches it and folds it back and stretches it, folds it back, and so on, and in the process the dough gets mixed up. And a very typical example is if he puts, for instance, cumin seeds or something like that in this dough, then gradually it gets mixed up so that the seeds are uniformly distributed in the entire dough. And this transformation I am going to talk about mimics just that. What happened in the Bernoulli shift was exactly that in some sense. What you did was, let me draw the map here. In the Bernoulli shift the map function itself looked like this, 0 to 1. We had something which was stretched to twice its length by 2x, and then you cut off that piece and put it back here. So that amounted to saying I start with a unit interval 0 to 1 and I stretch it to double its length, and it goes up to 2, and then I cut that piece and put it back on top of this. So this is essentially what happened, and then you had one piece here and another piece lying immediately on top of it in that sense. So this piece was put down here, and that is how you got the non-linearity here. in this map. So what has happened is that you stretch this dot and then you cut it and put it back here. You could have done the other thing, you could have stretched it and folded it back, and then what would that map correspond to? If I took this piece and instead of cutting it and putting it back here, I just fold it back in this fashion, then of course the map would look like this. It would be this piece and then it is folded back on this side. That is also non-linear. This map has the advantage that it is continuous, unlike the Bernoulli shift which was discontinuous at half. This is continuous and it has got exactly the same properties in many senses as the Bernoulli shift. The Lyapunov exponent is still log 2 because the slope is still 2 in magnitude, and the function is of course 2x here, and then on this side it is twice 1 minus x, 2 minus 2x. So this map is called the tent map. It looks like a tent, and it is also fully chaotic. Its iterates also fill up the unit interval densely for arbitrary typical conditions, and again once again all the rational points would lie on periodic orbits which are unstable. Now what the Baker map does is to take this idea of the Bernoulli shift and increase the number of dimensions of the map by 1 in such a way that the measure is preserved. So let me write this down and then we draw a picture to see what the transformation does. So it has got two variables now, and it says xn plus 1 is twice xn modulo 1, that is the same as the Bernoulli shift in this fashion, and then yn plus 1, this guy here, is equal to 1/2 yn provided xn is less than half and it is equal to 1/2 plus 1/2 yn if xn is greater than half. So you have two variables now, x and y, and what you are doing is to take the unit square in the xy plane and mapping it onto itself in a non-linear fashion, but a very strange non-linear fashion by these rules. And what does this look like? Well, now it is hard to draw because I can't draw xn plus 1 versus xn. So what I do is I draw a picture of xn and yn, and in the next picture I draw xn plus 1 and yn plus 1. So here was xn and yn, 0 to 1, 0 to 1. This is the y variable and this is the x variable, and what does this map do? It takes this square and it says expand in the x direction by twice, a factor of 2, and simultaneously contract in the y direction by a factor of half. So in the first step this map would go into something which looks like this. This is 0, this is 1, this is 2, and this is the y direction, it has come to a half here. And then it says the y variable, however, first of all you have to do a modulo 1, so it is clear that you have to cut this and put it back, but the way you put it back is you take it and put it on top there, and then in the second stage it does this. So this piece is cut and put on top of it. So as you can see, all points x which were less than half are still here, they are now between 0 and 1. All points x which are greater than half were here on this side, but the moment you have xn bigger than half, you add a half to yn, so you add this piece, this much is added and then it is put on top here. So it is clear that what has happened in this picture is if you started with a point say between 0 and half and here, and y also less than half, let me some point here, that point would have first gone to twice its distance and come down to half its height, and then it would remain here. On the other hand, if the point were here, this would have again done the same thing except it have gone here, and now it has come up and therefore it is moved there. The point has ended up there. So all points in this side have actually ended up there, and all points on this lower half, left half of this, have ended up at the bottom here. So everything in this shaded region has moved to this shaded region, but the area has been preserved. You started with unit area, unit square, and you still have a unit square. So therefore the Jacobian of this transformation is +1, is 1. So in that sense this map mimics a Hamiltonian system, because the measure is preserved, but is there a Lyapunov exponent? Is there loss of information? Definitely there is, because as you can see in the x direction it is like a Bernoulli shift. The y direction is compensating in the other direction to make sure that the volume area is kept constant. This system has two Lyapunov exponents because there is an x and a y. And what are the Lyapunov exponents? Log 2 is certainly one of them, and what is the other one? Yeah, log a half, which is minus log 2. So the sum of the Lyapunov exponents actually becomes 0, and that is characteristic of a Hamiltonian system always. As soon as measure is preserved, the sum of the Lyapunov exponents has to be 0, because any volume element would, some of them would expand, some of them would contract. So volume element dV would have e to the power lambda whichever of the expanding directions, and then e to the minus lambda different lambdas times contracting directions. What is the Lyapunov exponent or Lyapunov spectrum for an integrable Hamiltonian system? All of them have to be 0, and the reason is if you had one of them positive you have chaos, and there have to be a contracting direction immediately to preserve the volume. So you can't afford to have even one of them positive because it is integrable, and therefore all of them have to be 0 since the sum has to add up to 0. So integrable systems do not have any Lyapunov exponents. The motion is on tori in action angle variables, and on a torus the angle variables increase linearly with time. Therefore two initial conditions would separate linearly in time, and the Lyapunov exponent for power separation in time is 0 automatically. So Hamiltonian systems which are integrable have all the Lyapunov exponents are 0. Those which are not integrable, for every positive Lyapunov exponent you have a corresponding negative one. They would occur in pairs such that the sum would add up to 0, and here is an instance of such a thing. The Lyapunov spectrum now, Lyapunov exponents are log 2 and lambda 2 equal to log half equal to minus log 2. Unlike the Bernoulli shift where I told you that it is not invertible, you can't tell you can go in the forward direction, but given a final point you can't tell, there is no unique pre-image, any number of pre-images. After n iterations there are 2 to the n pre-images. Is this map invertible? This map is eminently invertible. You can predict the future of every point, you can go back, I can tell you given any point here I can tell you exactly where it came from up there. It is also invertible, and yet it displays chaos. Yeah. Again, because in the x direction you are losing, the errors amplify. So it is a subtle point, but the fact is that in chaotic dynamics, unlike differentiable dynamics, in discrete time dynamics you may be able to write down the explicit solution to a map explicitly, but it could still be chaotic. That was not true in differential dynamics. You could not write analytic solutions, you could not write an explicit x as a function of t or y as a function of t for arbitrarily long t. In discrete dynamics that is not true, because in the Bernoulli shift I know that xn plus 1 is 2xn modulo 1. This would imply that xn is 2 to the n x naught modulo 1. So I have written the solution down explicitly, but all the same it is chaotic completely. There is an interesting way of seeing why there is no loss of any information at all in this Baker transformation, and that is the following. Let me start by writing x naught equal to 0.0 a naught, a1, a2 dot 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 dot, and y naught is 0 point b naught, b1, b2 dot dot dot, right, in this fashion. So that is my initial binary decimal representation for x naught and y naught. Each a naught, ai is 0 or 1, and each bi is 0 or 1. Now after one iteration, what happens to x1? This is 0 point a1, a2, a3 dot dot dot, but what is y1 equal to? Y1 depends on whether x naught was equal to x naught was bigger than half or less than half. If it is less than half, a naught is 0. If it is bigger than half, a naught is 1. So what does that tell you? So what is it? 0 point a naught, b naught, b1, b2, etc. becomes this. So this a1 gets transferred to this, the other place, sorry, a naught. So you have that information here. Another way of saying this is to pretend that I am going to write the number x naught by y naught in a strange way. So I put a decimal point and write a naught, a1, a2, etc., and I write this in Hebrew. So I write b naught, b1, b2 on this side. It is a by infinite sequence, and let me pretend that I represent the y variable by going to the left hand side and the other one from going from left to right or right to left. So if this is a representation of x naught, then the representation of x1 is dot 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 b2, b1, b naught, a naught, a1, a2 on that side. So you see, you haven't lost anything. What you lost in one case you got into the other, and therefore all that you do is it's still a shift. So you keep simply shifting the decimal point one place to the right, and that is what the action of this entire map is. And it has this very weird property that it is in fact a chaotic map, but at the same time it is measure preserving and it is invertible. The general rule is that to produce chaos in a one dimensional map, it has to be non-invertible, but in 2 and higher dimensions even invertible maps can produce chaotic behavior. So it is a little different from what happens in the case of differential dynamics. Okay. Let me look at one more map of this kind to show you how complicated the system can get. And the idea is to mimic what happens in Hamiltonian systems, and this is the famous Arnold cat map. And again it takes the unit square in x and y, and it does the following: xn plus 1 equal to xn plus yn, again modulo 1, and yn plus 1 equal to xn plus twice yn modulo 1, and that is all it is needed. So your map looks like this. It is the unit square, this is the y direction and the x direction, and this map says distort this in this fashion. So as you can see, what you are doing is to take this variable xy and you are applying to it a certain transformation which is 1, 1, 1 and 2. So that is the reason why xn plus 1 is found from xn and yn by applying this matrix on it, and the determinant of this matrix is 1. So it is plus 1, so it is orientation preserving, it is measure preserving, the unit square is mapped to the unit square, but what happens because of modulo 1 is that it is non-linear, very badly non-linear. So if you took this original square and you applied that transformation, you of course go out of the square in general, and it would be some weird thing like this. It would look like this. It would perhaps look like this. This would become parallel to it, and then maybe look like that. And now you are supposed to take that piece, and because of modulo 1 you cut it, put it back here inside, and you keep doing this over and over again, and the square gets completely scrambled up. And the reason it is called a cat map is because Arnold, when he first gave this example, drew the picture of a cat here, the face of a cat, and then of course after a few iterations you can't recognize the cat at all. It is a scrambled cat, it's completely scrambled and mixed inside. Now you can see in this map we can find what the eigenvalues of this matrix are, and these eigenvalues are related to the golden mean 1 plus root 5 over 2, and it will turn out that this direction, there is a stretching direction, there is an eigen direction of stretching, and there is a contraction direction going inwards, and every point is an intersection of a stable and an unstable manifold. Every point on this is actually a hyperbolic point. There is a stretching direction and there is a contracting direction, and because it is on its modulo 1, it is equivalent to saying that I put it on a torus. After all, saying modulo 1 on a unit square, a torus is formed from a square by identifying opposite ends, right. I start with a unit square and I put an orientation on it, and I say bend this and sew this onto this, stick it onto this, and then you get a cylinder. And then if I put an orientation on this, and after I form a cylinder I take the cylinder and identify ends, what do I get? A torus. So a torus is like a square lattice, if you like, it is completely periodic, and this is on a torus, and it is a map of the torus to the torus, it is called an automorphism, and it is hyperbolic. So this cat map has a very fancy name, it is an example of what is called a hyperbolic toral automorphism, because it brings it back to itself, but it is just a big name. But a lot of these maps have been studied as examples of simple models which mimic Hamiltonian chaos, and once again you can show that the invariant density in this problem is also a constant. The entire unit square, the square is completely uniformly filled up by the iterates of a generic point in this case. By the way, this particular map, you can have other integers here, these have other applications. This particular matrix is a very strange one. It also generates what is called a Penrose tile, quasi periodic tilings in 2 dimensions and so on. We will not get into that right now. Let me go back and show you another map which is very similar to the Bernoulli map but uses a slightly different representation of real numbers, and this is the map which Gauss first wrote down, and it is called the Gauss continued fraction map. And very similar to the Bernoulli shift, where we said write the number in binary and remove the first decimal, remove the first digit and put the decimal point and so on. Here what one does is you start with the number x naught and you can write this number as a continued fraction. Every number between 0 and 1 can be written as a continued fraction. If the fraction terminates, then it is a rational number. If it does not terminate and goes on forever, then of course it is an irrational number. So every number like this can be written as over a naught plus, in standard form it can be written as 1 over a naught plus 1 over a1 plus 1 over a2 plus etc., where a1, a naught, a1, a2 and so on are positive integers. Every number can be written in this form. If this thing continued fraction terminates at some point, then I would say the number is rational, because you can rationalize the whole thing and get it as a p over q. But if it goes on forever, it is irrational, and this is represented for ease of writing also written as 1 over a naught, the plus sign is put here, and Gauss's idea was very simple. He said from this you form an x1 which is equal to 1 over a1 plus 1 over a2 plus 1 over etc. So throw this out. So find a map such that this first a naught is removed completely. Now how do you do that? Well, it is clear that what you should do is to take the reciprocal of this number, throw away the integer part, right, and keep this portion, the fractional portion. So what is the map now? It says xn plus 1 equal to 1 over xn minus the integer part of 1 over xn. This is the integer part. That notation stands for the integer part of 1 over xn. And then you are guaranteed to get a fraction between 0 and 1 once again, right. And what does the map function look like? If I draw it as a picture, so here 0 to 1, this is a half, this is 1. Y equal to 1 over x is just a hyperbola, right, it is simply a hyperbola, and that hyperbola would cut the point 1 and it look like this. If I could expand this, it would be a rectangular hyperbola which goes along like this, and if x is between, x naught is between half and 1, 1 over x naught is between 1 and 2, and therefore you have to subtract 1 from it. In other words, you take this piece, cut it and put it back here. So this is what the piece would look like. And then if x naught is between 1/3 and a half, then of course the reciprocal is between 1 and 3 and you have to remove 2 from it. So when you subtract that and put it back, here is 1/3, so it looks like this, and then between 1/3 and 1/4 it would look even steeper, it would look like that, and you have an infinite number of branches of this map. So this keeps going, it gets more and more steep, and then infinite number of branches. So you can see it is a very non-linear map. The number of pre-images of any point is actually infinite. So if you give me any xn, if you give me an xn plus 1, there are an infinite number of xn's from which it could have come. So it takes this Bernoulli Shift, makes it much worse in some sense. Now the slope is obviously bigger than 1 everywhere, and because of that this map is certainly hyperbolic, and you can see all its fixed points are unstable, all the iterates fixed points are unstable and so on, and the map is actually fully chaotic. Now Gauss came across this in a very interesting way. He wanted to solve a problem in number theory, and his question was the following: I start with a number between 0 and 1, an arbitrary number, I take its reciprocal, throw the integer out, I take its reciprocal, throw the integer out. If I keep doing this a very long time, for a long time, what is the probability that the final number I get is less than some value alpha between 0 and 1? And he found the answer, and the answer he got was the probability that the final answer is less than some number alpha, which is between 0 and 1, is log 1 plus alpha over log 2. And he got so excited about this that he wrote to Laplace about it, saying he's found the solution to this. And now we can understand this in the language of dynamical systems. All we have to do is to find the invariant measure of this map, and once we do that, we can integrate this invariant measure up to alpha, and that should give you this answer here. So even though we are not Gauss, we can at least guess the answer knowing what Gauss did. So let us see if we can do this. What would be the Frobenius-Perron equation in this case? Rho of x would, oh, before I do that, let us look a little bit at the fixed points of this map, which are unstable of course. So here it is, this is the fixed point, this is a fixed point, this is a fixed point, and so on. What is the first fixed point of this map? How would you find it? Well, this fixed point must satisfy x equal to 1 over x minus 1, right? And that solves to x squared plus x minus 1 equal to 0. So x equal to minus 1 plus or minus square root of 1 plus 4 is 5 over 2, and of course you want the positive root between 0 and 1, so it is really root 5 minus 1 over 2. That is the fixed point. Does that ring a bell? This is the golden mean, this number is the golden mean. So it is clear that it is coming out in a very natural way here. What is its continued fraction representation? Because that is very easy to find from this representation. It says 1 plus x equal to 1 over x. This implies x equal to 1 over 1 plus x equal to 1 over 1 plus 1 over 1 plus x, and so on. Keeps going forever. So this is in some sense the most irrational number of all, and the reason it is the most irrational number in a very precise sense is because you can see that if in a continued fraction expansion of this kind at some stage one of the a's becomes very large compared to 1, say 293 like Ramanujan found for pi after 3 or 4 such places, then you can neglect the rest of it and you have a very good approximation to the irrational number, a very good rational approximation. The Ramanujan actually found a rational approximation to pi with about 3 steps, but one of these numbers ended up being 293 or something like that, and therefore it is to a very large number of decimal places you had a rational approximation. But that fails completely when all these are equal to each other, and what is the smallest value that a can have? 1. So the moment you have 1s everywhere, this is in some sense the most irrational number of all, the one that is least susceptible to a rational. Where would you end this? At what stage would you end it? So root 5 minus 1, what is the value of root 5 minus 1? 0.618, yeah, good, it's worth remembering this number. That number 0.618 dot 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 etc. is in fact the golden mean, the most irrational one of all. What is this number? How are you going to find this? Well, I put a 2 there, isn't it? You subtract a 2, so you do this minus 2, so this is 2 plus x, and therefore that number becomes 2 plus 2 plus 2 plus and so on. And what will it work out to? We have to solve this quadratic equation, right? So what does that work out to? Square root of 2 minus 1 or something like that. It is called the silver mean. The other one is a golden mean, this is the silver mean. Next to this the original number, this is in fact a very poorly susceptible to a rational approximation. So you can see that as you go down here, this is a continued fraction expansion with 3's everywhere, 4's everywhere and so on. What sort of number is this? What sort of number would be x equal to 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2 plus 1 over etc. What would this be? Would it be a fixed point of this map? But what would it be then? Yeah, it would be a fixed point of the first iterate of the map or a period 2 cycle. So this number would alternate, there would be two, it's part of a period 2 cycle, one of which would start with a 1 here and the other one would start with a 2 here in the first place and so on. So you can actually generate all the periodic points of this map by this procedure, but they are all guaranteed to be unstable, and the question is what is the invariant density? For that we need to solve the Frobenius-Perron equation. So you have this equation rho of x equal to integral 0 to 1 dy delta of x minus f of y rho of y. But what is f of y? The map function, it is equal to 1 over y minus n, some integer n running from 1 to infinity, right? It is actually 1 over y minus 1 over this guy here, and this is n. You keep subtracting that for each of the branches. So what would this give you? If I write this out, this is equal to 0 to 1. This would be a sum from n equal to 1 to infinity because an infinite number of branches, and then an integral running from where to where? 1 over n plus 1 to 1 over n in this fashion times a delta function of x minus 1 over y minus n rho of y, that is equal to summation n equal to 1 to infinity. Now I have to convert this guy to a delta function in y. So let us write this as should have been minus n, so this is plus, sorry there is a minus sign here, so it becomes a plus. So this is equal to a delta function of 1 over y minus x plus n, and I need to convert it to a delta function in y. So what should I do? How do I do that? How do I handle a delta function of a function of the variable y? I have a thing like this. What does that stand for? It obviously contributes when you integrate in y wherever phi of y is 0. So at all the roots of phi of y it is going to contribute, correct. If I do an integral like this dy f of y, then this is going to have all those values corresponding to the roots of phi of y. It is going to pick up contributions from all the roots of phi of y, and assuming the roots are simple roots, which in that case it is, because y is equal to 1 over x plus 1, and there is exactly one root in each of those intervals of integration. So what is a general formula like this? What is the general formula? Integral dy delta of phi of y f of y, assuming that the interval covers the zeros here, is equal to what? Well, let y I be the roots of phi of y equal to 0. Let these be the roots. Near one of those roots I can do a Taylor expansion. So phi of y can be written as phi of y sub I plus y minus yi phi prime of y sub I plus dot 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 near one of those roots, but this is 0 by definition, and then this is the term that is picked up, and this is a constant, that is a constant. So you have a situation of delta of y minus yi times a constant, and what do you do with the constant? You pull it out. So this quantity here is equal to a summation over the roots, a function of yi divided by the Jacobian modulus delta of ax is mod 1 over mod a times delta of x. So you pull that out. That is why I needed simple roots, otherwise this delta function is not meaningful. So I need to use that here, I need to put that in here. If I do that, what's the Jacobian of this transformation? The derivative of 1 over y with respect to 1 over y squared. You take its modulus, it is just 1 over y squared, and you have to put y equal to 1 over x plus n. So what do you get finally? Rho of 1 over x plus n divided by x plus n whole squared. Right. That is the functional equation to which the Frobenius-Perron equation has got reduced, but this is not an easy equation to solve. I mean, you have a formidable task, because you have to find rho of x such that rho of x is summation n equal to 1 to infinity 1 over x plus n the whole squared rho of 1 over x plus n. This is the equation to which Gauss found a solution. Since we are not Gauss, we can try to find what the solution is by putting it in and seeing if it works or not. If we put rho of x is 1 over 1 plus x, it has got to be non-negative, it has got to be normalizable, it has got to be integrable from 0 to 1, which it is, and you have to normalize it. So what is the integral of this from 0 to 1? It's log 1 plus x, and then you have to put x equal to 0, x equal to 1, and then divide by the whole thing. So log 2 plus x log 2. So I leave it to you to check it out that this is true. Put that in and see if that really works. And you have to use this most complicated of mathematical tricks which you learn in the 3rd standard, called resolving into partial fractions. So you need to do at one stage you have to resolve into partial fractions, everything will cancel out and give you the answer. So this is the reason why Gauss was able to assert that the probability that the iterates x less than equal to some alpha equal to log 1 plus alpha over log 2, because you had to integrate this density from 0 to alpha, and then you got this log answer. So this was Gauss's discovery, and this map here is called the Gauss continued fraction map. What would be its Lyapunov exponent? The Lyapunov exponent, mind you, look at the formula we have for the Lyapunov exponent. We have lambda equal to integral, in this case 0 to 1 dx rho of x log modulus f prime of x. So you could regard this Lyapunov exponent as the average value of the log of the stretch factor modulus f prime of x. So you could regard it as that, because after all it is an integral over this probability density. So you could also take it to be average value of log f prime of x over the interval. Now what does the slope look like to you? It is clear that the slope is getting steeper and steeper and steeper, so it is not even clear whether this is finite. Some of these branches are becoming almost infinitely steep, and therefore you think the expansion rate is enormous out there, but the region in which it is happening is getting smaller and smaller. So there is a possibility that the whole thing will actually be finite if you integrate it out. So you put that in, and then what do you get here? This is equal to, well, f of x is 1 over x, so f prime of x is 1 over x squared, the modulus of that is equal to, so what should I write here, is equal to 1 over log 2, that is this portion that has come, 0 to 1 dx rho of x is 1 over 1 is 1 plus x, and then log modulus 1 over x squared, that is equal to minus 2 whatever it is, minus 2 log x. Is it positive or negative? It is positive. Log x is itself negative between 0 and 1, so the minus sign cancels out and it is indeed positive. You have to do this integral. This is not a trivial integral to do by elementary form means, because you can't integrate by parts, it will just get worse as you go along. It is one of those weird integrals which involves somewhat more complicated functions. This one involves zeta of 2, the Riemann zeta function of argument 2, and the final answer turns out to be equal to pi squared over 6 log 2. Those who are interested, I leave it to you to work this integral out, look up tables or whatever, but you can actually reduce this, do a binomial expansion of 1 over 1 plus x and try to integrate term by term, for instance, and then you end up with a series, you have to be worried about convergence and so on, but still the final answer is this, right. This combination pi squared over 6 is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared all the way to infinity. It is the zeta function at argument 2, and this is the answer. So it is bigger than log 2, this number. How big do you think it is? Pi squared is of the order of 10, and log 2 is like 0.7, so that is like 10 over 4, it is like 2 point something, 2.3 something. It is bigger than log 2, much bigger than log 2. So it is in fact a very, very hyperbolic map, as you can see. And unlike the earlier cases, the map is not uniform in the sense that it does not have a constant slope, the slope goes on changing, and finally the average value of the slope over the invariant measure turns out to be that number, the log of that turns out to be that number. You can do a lot more with this map, but I do not want to get into further details here. Let me return to somewhat more general considerations. One of the things that we are going to be interested in statistical physics is, given this kind of complex dynamics, it is clear now we can do much more with this. The subject by itself will take off from here, and one can study the various kinds of mixing properties, ergodicity properties and so on of various dynamical systems, look at intermittent cases, look at more complicated situations and so on. But what we would like to do is to turn our focus slowly towards statistical physics. For this we need to have some inkling, some general theorem, some general idea of what the behavior of these systems is going to be like in phase space. A very relevant question is the following: here is my phase space and I am going to assume that the system is ergodic, even chaotic in general. Then an initial volume element here is going to get scrambled up, get mixed up, badly twisted around and so on and so forth in a very, very complex fashion. I could ask, if the system is ergodic, then I know that portions of this initial volume element would return after a certain amount of time to this original place, wherever the original location was. So I ask the following question: what is the time of return on the average? And this is called the recurrence time. What is the mean time of recurrence? I am guaranteed there is going to be recurrence. So the question is, what is the average time it would take for things to come back? Now that question can be answered precisely, and what one does for that is to partition the phase space into cells. So this is a typical cell in phase space. Assume that this dynamics has an invariant measure, in the sense that as the dynamics keeps going you end up with some invariant density or invariant measure of a cell. Let me call this cell C, label it C I, C sub I runs over all the cells, and I ask, and its measure is mu of Ci. If you like, if the system has an invariant density rho of x, integrate rho of x over the volume of this cell, and that is the measure of this cell, it is the invariant measure. And now I ask, suppose I start with my representative point in this cell Ci. As time goes on it moves out of this cell, it wanders around and it would return to Ci. If it gets back into Ci somewhere, I call that a recurrence. So I start here and maybe it does this, comes back here, I call that a recurrence. In fact it is the first recurrence, and because the system is ergodic and ongoing, it would again wander around and then come back. It will not intersect itself, but this is in a higher dimension. I call that the next recurrence, and so on. I could ask then, what is the mean time of recurrence to come back here, and there is a very general formalism which helps you to calculate this number without any ambiguity at all. So we can ask for mean time. I do not want to go into this algebra because it requires a little bit of manipulation of integrals, but instead of doing that, let me just quote the answer, and it is not very hard to derive. I will give in a problem sheet, I will give you sufficient input in order to be able to derive this result yourself. Poincaré derived this in the late part of the 19th century, or maybe beginning of the 20th century, and the mean time of recurrence to Ci, let me call it T Ci average mean over all realizations. Sometimes it could come back fast, sometimes it could come back much slower depending on where it started, etc. But over a long period, long time average over the invariant density, what is the mean time of recurrence? This turns out to be equal to is proportional to 1 over the measure of this cell. So it is a very simple formula. Okay. The numerator would be your time step tau, whatever that be, however small it is. So it depends, the units of time of course would depend on your time step, but the mean time is proportional to the reciprocal of the measure of the cell. This of course tells you, this reciprocal tells you the larger this measure is, the shorter the mean time is, and as you can see it is equal to 1 if you look at the full phase space. The system is there somewhere, so in one time step it is still there, and that is the end of it. But as it gets smaller and smaller, as the cell gets smaller and smaller, or at least its invariant measure gets smaller and smaller, this number becomes larger and larger. And if it is a point, if it is a single point, then this becomes infinite, which is as it should be, because it tells you there is not periodic motion, this is chaotic motion. So really there is no period here at all. So what is being understood here is that on the average, as the measure of the cell gets smaller, as you refine your coarse graining here, the recurrence time will naturally go up more and more. But it is not just the physical volume in phase space of the cell that is important, it is actually the invariant measure. It depends on how much time is spent at various points. When we wrote down all those invariant measures, the rho of x, you can actually ask what fraction of time does an iterate of an arbitrary point spend between some region to some other region, and that is proportional to the measure of that cell directly. So this thing here is called the Poincaré recurrence formula or theorem or whatever you call it. Such a recurrence is called a Poincaré recurrence. Yeah. Pardon me? I have to average over what? This is already an invariant measure, so its average. The question is, what are these? What is this average over? This average is over all realizations of this process. So you have to start at this point, at this point, at this point, at this point. You have to start everywhere, and each time you have to find all the recurrence times and then average over it. Yeah.
Ergodic, you start at one point and then take time to infinity.
It's not clear. So it depends on how close this is. It depends on how refined this coarse graining is. Right. If it's extremely refined, there's no reason why one portion and another portion should have exactly the same recurrence time. Not at all. So even within this cell, the invariant density may be weighted more towards this point than this point, definitely. So now we are getting into the fine nitty-gritty of how is this coarse graining done and so on, right. So in general, in the most general case, this thing here would be typical cases. If it is sufficiently hyperbolic, sufficiently chaotic, then it doesn't matter where you are inside the cell. This point is that wherever you start, it would be equivalent to starting anywhere else in this cell, but this would really depend on what you call a cell. The most convenient thing to do would be to see how random this could get. It would be very nice if you could partition this cell into such, partition the phase space into such cells that the entire process, the dynamics, is mimicked by a random process. Like in the earlier case we said this random process could be, for example, coin toss. If it is mimicked by what is called a Markov process, then we can write the answer down completely. We can write down the measure, we can write down the mean, we can write down explicitly what the formulas are, because then for a Markov process what you do is the following: you assume that each of these cells represents a state of the system, and then you say that the transition probability per unit time from any state to any other state is prescribed to you, and if it is a Markov process, the probability that you go from any given state to any other state in n time steps would be related to the nth power of this transition matrix, some suitable element of the nth power of the matrix of transition probabilities. And that is a property of the Markov process, and if you have a partition of that kind, it is called a Markov partition. Okay. One would like to see if in general cases you can produce Markov partitions, because you would also like to use the power of probability and statistics in order to solve dynamical problems. The other thing you can ask is, I do coarse graining in phase space, so clearly I am losing, I am blurring information, but once I have done the coarse graining, can I reconstruct the trajectories completely from the coarse grained information? And that is an interesting question. Let us go back and look at the Bernoulli shift. In the Bernoulli shift, the coarse graining that I suggested was you took 0 to 1 and this was a half. I said call this L and call this R, call the bin from 0 to half L and half to 1 R, and then as you iterated you just kept track of whether the point of the iterate was in L or in R, and you had a string of L's and R's. But you see the L's and R's corresponded to whether the AI's were zeros or ones. So if you give me the L's and R's, I can give you the A's completely. I can regenerate the original dynamics from the coarse grained dynamics. A thing which does that is called a generating partition. Because the dynamics of the coarse grained dynamics, which is called symbolic dynamics, because you have an alphabet with 2 letters L and R. So keeping track of just the L's and R's, if you are able to reconstruct what the original trajectory was, the original point was, then you got a generating partition. And of course this would be the dream of in every system, to discover a generating partition would be wonderful. Or in the absence of that, if you look at Markov partition, where the entire process of transitioning from one state to one cell to another is simply replaced by a Markov process with some prescribed set of transition probabilities. Of course it would be a wonderful thing if you could have a generating Markov partition, then of course the problem is solved completely. But these are approximations in general, it is not easy to find in higher dimensional dynamical systems things of this kind, but they provide the starting point for this whole subject of symbolic dynamics. There is a large literature on this, it is a subject by itself. You could ask what happens in Hamiltonian dynamics, what sort of behavior do you have when you have chaos in Hamiltonian dynamics. It turns out that Hamiltonian dynamics, when it becomes chaotic, is so complicated that in the vicinity of the chaotic points you can do symbolic dynamics and transform everything to things which look like Bernoulli shifts, but the alphabet you need is itself infinite. You cannot map Hamiltonian dynamics, coarse grained Hamiltonian dynamics rigorously to symbolic dynamics with a finite alphabet. You actually need an infinite alphabet. So you can imagine how complex the system is, how complex Hamiltonian dynamics is, how delicately balanced integrability is. When you see that as soon as you lose integrability, you have enormous complications, okay, this kind. This takes us into many other things, and I will slowly move into statistical physics from next time. In particular, when you look at molecules of gas in this room, you ask what is the behavior like. The answer is it is chaotic. Even in Newtonian dynamics it is completely chaotic. What is the Lyapunov exponent like? Remarkably enough, the Lyapunov exponent is like the number of degrees of freedom, and that is of the order of 10 to the 23. Now we are talking about Lyapunov exponents log 2 and pi squared over 6 log 2, that is of order 10 to the 23 in principle. What is the Poincare recurrence time like? Well, now this will depend on how closely you are watching your system, how much coarse graining you are going to do. The exact recurrence time, it will depend on the size of your phase space, how many degrees of freedom you are willing to put in, but you can also show that if you are going to look at the micro states of the system, namely I am going to look at the state of every particle in this room and call that a state of the system, then the Poincare recurrence time becomes of the order, this becomes of the order of e to the power the number of degrees of freedom. So that is like e to the power 10 to the 23. This is a staggeringly large number, inconceivably large, and that is why things look irreversible to us. It is one of the reasons why you have irreversibility appearing even if nothing else happened, and that is because things are never going to look reversible, because the Poincare recurrence time is actually so large. So if the observation time is much smaller than the recurrence time, things could look irreversible even with reversible dynamics going on, and e to the 10 to the 23 is so large that I do not bother to write down the units. whether I measure it in femtoseconds or in ages of the universe, it is only a matter of 10 to the 42 or 10 to the 32, that is nothing compared to, so even the units do not have to be written down. So this is just completely outside the scope of reality. It is really an irreversible system because of the very large number of degrees of freedom. We will see how some of these concepts play a deep role in our understanding of statistical physics. I am going to assume a certain knowledge of thermodynamics on the part of all of you. We will however revise thermodynamics in 15 minutes and after that go on to elementary statistical physics. So this is what I will start with next week. Okay. Meanwhile, I will give you another problem sheet which I put down some of these ideas, and in particular how to derive this relationship here, which is very easy to do, but you need a little bit of algebra, and also you can do more things. The formula that you derive, you can also ask what is the mean time to escape from some cell, what is the mean exit time, what is the mean return time, what is the mean time to go from one place to another, and so on. All of these can be answered fairly straightforwardly once you have some information about the invariant measure of the system. So let me stop here today.